Our speaker this week is Dr. Pantelis Pnigouras, and he will talk about secular instabilities in neutron stars. But before he does this, I will shortly introduce him. So I know Pantelis from my time in Tübingen, where we overlapped in the group of Kostas Kokodas. So Pantelis is currently a research fellow in the relativistic astrophysics group at the University of Southampton in the UK, where he's in the group of Professor Niels Anderson, that many of you probably know from his work on neutron stars and black holes. Pantelis obtained his bachelor's degree in Greece at the University of Thessaloniki, Aristotle University, and then he went to Germany in 2011 to join the Kostas Kokodas group in Tübingen. There he did his master's degree and also his PhD. His thesis has been evaluated very, very well. Thesis was also awarded the so-called thesis prize, which also includes that the thesis is actually printed in a hard copy commercially that you can actually buy in libraries buy. So this was a very nice thing. And then after his PhD, he moved to, he stayed for a short postdoc in Tübingen, and then he went to Southampton. In his PhD, he was working on the saturation of the F-mode instability, and now more recently he's working on tidal deformability and gravitational-wave driven secular instabilities of neutron star binaries. And this is, well, at least the secular instabilities, this is what he will talk about. So Pantelis, I'm happy that you accepted the invitation. I'm looking forward to hear your talk.
Okay. So first of all, let me try to share my screen. Can you all see that?
Yes.
Yep.
Okay. So first of all, thanks, Sebastian. Thank you for the invitation in this seminar. I know it's not directly in the interests of the group, the topic of this presentation. So I'm going to do my best to keep it simple, and basically it's just going to be a short review of the subject, and just in the end I'm going to bore you with some of my most recent research on this. And of course, feel free to interrupt me with questions if something doesn't make sense, or if you want any clarifications. I think it would be better this way. Okay, so I'm going to explain what the title is during the presentation. But first, I'm going to start with an old question. I'm going to take you back to the work of Newton, who in his Principia, he was the first to rigorously address the question, what is the shape of a rotating self-gravitating body? And basically the question at the time was formulated as, what is the shape of the Earth, of the rotating Earth? And what Newton did is he modeled the Earth as a homogeneous, slowly rotating body, sphere. And he showed through a thought experiment that the Earth, the slowly rotating Earth, has to be an oblate spheroid, which nowadays seems obvious, of course, but at the time it wasn't, as you can see in this nice caricature here. You can see my mouse cursor, right? Or
yes, I can see it.
Okay, I haven't used Zoom before, so sorry. So yeah, it wasn't obvious at the time, and Newton was the first one to actually kind of prove this. And later on, there were actual experiments involving the measurement of the gravitational acceleration at various regions of the Earth, and they actually confirmed this picture that the rotating Earth has to be an oblate spheroid. And it led to this amusing quote by Voltaire, You went out into the wilderness to confirm what Newton knew without leaving home. This work was continued by Colin McLaren some 50 years later, who actually showed, he proved this analytical formula connecting the angular velocity of the object with the eccentricity. And this is an exact formula, and it applies to a homogeneous spheroid with some density rho, angular velocity omega, and eccentricity e. And this in fact confirmed that what Newton showed for a slowly rotating Earth, that no matter how fast the body rotates, it has to be an oblate spheroid. And this formula here is plotted here, this line. So this is angular velocity normalized to some units versus the eccentricity. So far, nothing surprising really, except a century later, Jacobi and Meyer, or I think it should rather be Jacobi, I think he's German, they showed, surprisingly, that there is another possibility that a rotating body can also assume the shape of an ellipsoid, not a spheroid. So it would have three unequal axes. And this is quite counterintuitive, I think. And in fact, they showed that the so-called Jacobi ellipsoidal sequence bifurcates from the McLaren spheroidal sequence at some eccentricity at 0.81, so around here. So after this eccentricity, you have two possibilities. Either the body remains a McLaren spheroid or it becomes a Jacobi ellipsoid. And I found this nice video showing this. So now we are going up this curve. Here, the angular momentum is constantly increasing. And at the bifurcation point here, you start going to the Jacobi sequence. So now the angular velocity is decreasing. And I'll just play till the end because it's quite funny. This is, of course, theoretically possible. I mean, from common experience, we know that this doesn't really happen. But theoretically, it is a possibility. And this is what Jacobi and Meyer showed. And later on, Dirichlet and Dedekind showed that there is even a third possibility, which is again a spheroid, again an ellipsoid, sorry. But this time, this ellipsoid doesn't have rigid rotation. So if you can imagine this, this ellipsoid is basically stationary in space, and it preserves its ellipsoidal shape just by internal fluid motions. And the Dedekind ellipsoids are congruent to Jacobi ellipsoids. That basically means they have the same shape and size. So they look identical basically, except the Jacobi ellipsoid, you can see it rotating. The Dedekind ellipsoid is stationary. So we have three possibilities: Dedekind ellipsoids, Jacobi ellipsoids, and McLaren spheroids. The question is, which one is our body going to assume in the end? Which shape is it going to take? And this depends on the presence of dissipation mechanisms. And it was Thomson and Tite who first mentioned this. Thomson is Lord Kelvin, actually, who in their seminal work, a treatise on natural philosophy, they are the first to mention that if there is any viscosity in the body, the equilibrium shape that is going to assume cannot be secularly stable. So that means that our body starts as a McLaren spheroid, and as rotation, as the angular velocity increases, then past the bifurcation point, if there is viscosity present, it's going to become a Jacobi ellipsoid. And that is because the Jacobi ellipsoid has a lower energy than the corresponding Maclaurin spheroid in the sequence. And it's basically more favorable for the body to admit such a shape. And on the other hand, for Dedekind ellipsoids, the corresponding Dedekind ellipsoid in the sequence has a lower energy and angular momentum than the corresponding Maclaurin spheroid in the sequence. And viscosity doesn't allow the transition at this case, because viscosity conserves angular momentum, but gravitational waves do. So in a nutshell, past the bifurcation point, if the system emits gravitational waves, it will tend to become a Dedekind ellipsoid. And if there is viscosity present in the system, it will tend to become a Jacobi ellipsoid. And here we have another way to parameterize rotation, which is this parameter vita. It's the ratio of the kinetic energy to the gravitational energy of the body. And the bifurcation point that I showed you earlier, this one at eccentricity equal to 0.81, corresponds here to vita equals 0.14. And this point is surprisingly independent of the structure of the body, of its equation of state, as I'm going to describe later what the equation of state is. This is basically what the concept of secular instability is all about. So it's not a fluid instability in the sense that the system is unstable due to an oscillation and it breaks up. It is an instability related to a dissipation mechanism, to the presence of a dissipation mechanism. And secular is basically a fancy word for slowly evolving, because these dissipation mechanisms, either gravitational waves or viscosity, they evolve on longer timescales than the dynamical timescale of the body. And so we have these three possibilities. Of course, in real systems, both gravitational waves and viscosity tend to be present. And then it's just a competition between the two. So if gravitational waves prevail, then the body will tend to become a Dedekind ellipsoid. If viscosity prevails, then the body will try to become a Jacobi ellipsoid. And if they are equally important, then you can evolve all the way up to the Maclaurin spheroidal sequence, up to the dynamical instability point, which is now a pure fluid instability, not related to any dissipation mechanism. But you need really fast rotation for this. And this is the dynamical instability. And as people showed years later, all of these instabilities are actually related to oscillation modes of the body. In our case, quadruple F modes, which I'm going to present briefly now. So we're going to talk only about fluid modes. So we're going to take a fluid body and see what oscillation modes it has. So the general idea, the general categorization of modes is we take a generic perturbation Xi on the equilibrium, and we decompose it into vector spherical harmonics. And if we do that, we can see there are two types of modes. We have polar modes and axial modes. The polar modes are easier to picture. They're just, you can imagine the sphere oscillating up and down in various parts, and then you have the various degrees and orders for the spherical harmonics. So these are basically density perturbations of the body. Whereas the axial modes, they are velocity perturbations that occur on equipartition surfaces on the sphere. So you don't see any actual deformation. It's just there are perturbations on the fluid itself, on the velocity field. And as we said before, we have the F mode. This is a polar mode, and it's the fundamental mode. It's like when you have a string and it oscillates all together up and down. This is the zeroth overtone, if you will. And it's essentially it's a surface gravity wave, corresponds to overtone equal to 0, and its eigenfunction can be seen here. And then you have overtones of the F mode, which are two types. First, you have P modes, which are sound waves. So the restoring force is pressure. And you can see two of their eigenfunctions here. And their frequencies increase as you increase the overtone. And then you have G modes, which are internal gravity waves. So the restoring force is buoyancy, basically. And their frequency decreases as you increase the overtone. So you have overtones on both sides of the F mode. G modes do not occur in all stellar models. You need to account for some buoyancy in your star to actually have G modes. This can be a temperature gradient, or it can be some composition gradients in order for buoyancy to appear during the oscillation and act as a restoring force. And then you have axial modes, which are, they are called R modes, and these are basically inertial waves. These are similar to Rossby waves on the Earth. So types of waves you have from hurricanes and atmospheric movements of sorts. And the restoring force here is the Coriolis force. And as we said, these do not cause any deformation on the star. They're just perturbations of the velocity field of the fluid. And finally, you have inertial modes, and these are have both polar and axial components. And this is basically the zero buoyancy limit of R and G modes. So if you don't have buoyancy in your star, the G modes somehow merge with the R modes, and then you can see inertial modes on the star. And for R modes and inertial modes to appear, of course, you need rotation. You need your star to be rotating, because they are restored by the Coriolis force. Now, the interesting stuff happens when you introduce rotation. And of course, you expect all stars to rotate to some extent. So when your star is not rotating, your mode corresponds just to one number. So all spherical harmonic orders are degenerate, and they all correspond to the same frequency. So this is now for L equals 2. So you have all the M's are between -2 and 2. And as you introduce rotation, it's like the Zeeman effect in atomic nuclei. As you introduce rotation, you can see that the different M's now correspond to different frequencies. And as we increase rotation more and more, the splitting increases. And here to show this, I've used the so-called slow rotation approximation, which is you treat rotation perturbatively. It's not very accurate, but it gives you an idea. And the dashed lines correspond to first order corrections, which is why they're just lines. And then the solid lines correspond to higher order terms. And what you can see here that's interesting is this one, which is the retrograde mode. I should have said that the different M's correspond to modes traveling in opposite directions in the star. So the negative M's here travel on the same way as rotation on the star. and the positive m's travel on the opposite way of rotation, which is why they're called retrograde. And if you see here, this is the frequency that we would detect if we observe the star from a distance. At some point, the frequency of the mode can become 0 and even negative. And just to give you a picture of this, so the red line here that moves around the star is, this shows how the star is rotating. So the star here is rotating anti-clockwise, but our mode, which is the deformed star, rotates in the other direction as long as the mode frequency is positive here. If you go to the point where the mode frequency becomes 0, then all you see is just a stationary ellipsoid, basically. The star still keeps rotating in the background, but the mode reaches a point that appears stationary because it's dragged forwards by the rotation of the star. And when the frequency of the mode becomes negative, you see that it follows the rotation. So the mode from being retrograde here, it becomes prograde here. So now it follows rotation. And based on the discussion we did before, all this shows is that at this point, when the frequency of the mode is 0 in the inertial frame, the star basically becomes a Dedekind ellipsoid because it's stationary. All you can see is a stationary ellipsoid. And this is the way people showed that actually these instabilities are related to oscillation modes. So here we checked the L equals 2 F mode. The prograde mode is the M equals -2, this one. The retrograde mode, the one we're concerned with here, is the M equals 2. And the retrograde mode is what causes the instability towards the Dedekind sequence. So the instability driven by gravitational waves. And the prograde mode, if we do something similar, we will see that at some point, the prograde mode would appear stationary on the rotating frame. So it would travel at the same rate as rotation if you were standing on the star. So if you were standing on the star, you would see the mode just standing still. And this is the point where the star becomes a Jacobi ellipsoid. And this is the instability associated with viscosity now. And you can also see this here in this diagram. This is the parameter beta we talked about earlier. This is the pattern speed of the mode, just its frequency divided by the m. And this is the retrograde mode. This is the point where the secular instability sets in. And past this point, the mode is unstable to gravitational waves, the retrograde mode. And here, past this point, the prograde mode becomes unstable to viscosity. And past this point, we have a dynamical instability, but we're not going to talk about this. For reasons I'm going to explain later, the gravitational wave driven instability has attracted the most attention. And this is what we're going to talk about basically in the rest of the presentation. But first, let me give you a nice mechanical example. It's a really old one, and with which one can illustrate nicely, we can present a mechanical analog of the viscosity-driven instability. So imagine that you have a spherical ball like this, which is rotating around this axis, and you put a particle inside, just a marble or something, and then you solve for the equation of motion along the direction theta, which shows how far away from the axis of rotation the particle is. And if you solve this equation for if you find from this equation the equilibrium points, you will find that there is an equilibrium point at 0 at the bottom of the ball, very logical. And there is another one which is further up the ball and is only allowed if the angular velocity with which the ball is rotating is larger than some value. And this is where the analogy comes in, because what happens is that if you also work out the stability of these two equilibrium points, you will see that the two equilibrium points exchange stability at this point. So it's a bifurcation point. So if your angular velocity is below this value, then the bottom equilibrium point is a stable one. And if you are past this value, then the higher equilibrium point is the stable one. And you can see this better if you include friction in your equations, which is, let's say, the analog of viscosity in our case. So if you do that and you solve for the oscillations of the small particle, what you find is that your prograde mode, so you find two modes of oscillation, one that is one where the small particle rotates together with the ball along the same way with rotation, and the other one, it goes the other way. And what you find is that the prograde mode, so the one that goes against rotation, is damped by friction unless you go past this value here. And if this happens, this exponential becomes positive. And what it does is it drives the particle slowly from the lower equilibrium point to the higher one. So friction here works not as a damping mechanism, but as a growing mechanism for the oscillation. And to complete this analogy with the viscosity-driven instability, at the bifurcation point, the frequency of the oscillation equals the angular velocity of the ball, just like the situation we have in a Jacobi ellipsoid, where your oscillation mode travels at the same speed as rotation. Okay. So as I said, the gravitational wave instability has attracted the most attention. It was discovered much later than the viscosity-driven instability, and it was Chandrasekhar in the 70s who proved that macro-N spheroids should be unstable to gravitational wave emission, and they should be driven towards the Dedekind sequence, as I mentioned before. And a few years later, Friedman and Schutz showed that this instability is actually generic. So what this means is that what we talked about was the L equals 2 mode. That's the one we showed, the L equals M equals 2, the retrograde F mode. But what they showed is that for any angular velocity of the star, there should always be a mode driven unstable by gravitational wave emission. And what this means is that even if you remember from here, the L equals 2 F mode becomes unstable at quite high rotation rates. So you need to go past the limit. You need to be close to the limit where the star actually breaks up due to rotation. This is the normalization here. It's called the Kepler frequency. And past this frequency, the star basically destroys itself due to the centrifugal forces. And for the L equals 2 F mode, you need to be close to that limit for the star to become unstable. But there are higher order modes, for example, L equals 3, L equals 4, L equals 5, which can become unstable much, much earlier. And Friedman and Schutz actually showed that there should always be a mode for any angular velocity that is driven unstable. And the way you can show this is if you calculate the mode energy rate due to the emission of gravitational waves. So as gravitational waves are emitted from the body, the energy of the mode changes. And this is what you get if you expand it in mass and current multiples. So mass multiples are related to density perturbations, current multiples are related to velocity perturbations. And you have this factor here. This is the frequency of the mode on the rotating frame, which depending on the convention you use, we're going to assume that it's always positive. And this factor here is the frequency of the mode in the inertial frame. So now, if your mode changes frequency in the inertial frame, like we saw before, if this becomes negative, then this whole thing becomes positive, and instead of gravitational waves dissipating the energy of the mode, they increase it. And this is where the instability due to gravitational waves sets in. The most susceptible modes to this to the so-called CFS instability from Chandrasekhar, Friedman, and Schutz are the F modes and the R modes. The F modes, because they are the biggest deformations of the star, so they have no nodes. They're the fundamental oscillation modes. So the deformation that they cause is bigger, and thus they emit gravitational waves much more efficiently. And R modes, because R modes actually are unstable always, pretty much, even though they do not emit gravitational waves as well, because they emit through the current multiples. They don't have any density perturbation, so they don't cause any actual deformation on the star, but they still emit some gravitational waves. But the big advantage, if you like, for the R modes is that they're pretty much always unstable. And the stars where this can happen have to be fast rotating and compact. Fast rotating because, as we said, for the F mode, you need quite high rotation rates in order to achieve to get past the instability point. And compact because you need an efficient emission of gravitational waves for the instability to work. And nature provides these stars in the form of neutron stars. And the systems that astronomers are particularly interested in are accreting neutron stars and newborn neutron stars, because these are the ones that rotate the fastest out there. And the most recent studies have shown that such signals from unstable modes could be potentially detectable with current gravitational wave detectors, but unfortunately from not very far away, so from within the local galactic group. Another interesting possibility would be from neutron stars that you get after a merger of two neutron stars. So if the neutron star you get after the merger remains stable long enough, then you can get such modes becoming unstable very fast and very, well, the evolution of the instability is very fast in these stars. And in this case, we showed that such sources could be detectable from within the Virgo cluster, so a lot further away, thus giving a chance to this generation of detectors to maybe locate such a source. And the reason why this is interesting is because from such signals, you can get very much information about what the star is made of. So the so-called equation of state of the star. And this interests more people than just astronomers, because the neutron stars basically contain matter at conditions that cannot be easily reproduced in experiments, such as in particle colliders, etc. So basically, we don't have enough information about the dense nuclear matter equation of state, and such signals could help constrain or even derive the equation of state of the neutron star. And what you do usually in this case is the information you get from the signal is some measurement of the density of the star or the average density. And then depending on how much else information you have about the source, you can derive a constraint about the radius of the star. And then you can in some way reconstruct the equation of state in the mass radius diagram. So if you know the mass of the star and the radius of the star at sufficient accuracy, then you can reconstruct the equation of state and then compare it with theoretical models such as these and rule out equations of state, etc. So the current constraint, the main constraint we have nowadays is that the equation of state has to reach the 2 solar mass limit. And if the recent source detected by LIGO is a neutron star, the 2.6 solar mass one, then all these equations of state would be ruled out, everything that is below 2.6. So this is the way we could learn something about the equation of state of the system. And there are more fancy ways, like people have derived empirical relations, which are equation of state independent, and then you can remove some degeneracies from the problem, and from this derive information like density, radius, or moment of inertia of the star, etc. And you can also find out information by studying the evolution of the star itself. And for example, if the star has an unstable R mode, then the evolution of the star through the instability region, for which I'm going to talk about in a minute, tells you a lot of information about what the star is made of. But in any case, you need a combination of gravitational and electromagnetic observables to reach reliable answers. And this is what I was talking about before. So basically, from what I've told you so far, you've probably understood that in order for the instability to be active, you need to be above a certain angular velocity. So your star needs to be rotating at some minimum angular velocity for the instability to occur. However, this instability is suppressed by other mechanisms in the star, and the main one is viscosity. So viscosity acts against the instability, and if you take the formula I showed you before about the energy rate of the mode due to the emission of gravitational waves, and you also take into account the energy rate of the mode due to viscosity, then you can find a region in the angular velocity temperature space where the instability is actually active. So if we didn't have viscosity, then this region would this would be just a straight line, a horizontal line, and above this line you would have an instability. But now viscosity, because it's temperature dependent, viscosity becomes strong at low temperatures where shear viscosity dominates due to particle scattering, and at high temperatures due to bulk viscosity, which is due to matter driven out of beta equilibrium during the oscillation. So at these two areas, at low and high temperatures, the instability is completely suppressed. And what you're left with is an area around 10 to the 9 Kelvin, where your mode, your star will be unstable to gravitational wave emission. And here you can see the instability windows, as we call them, for 3 F modes, the quadrupole, the octupole, and the hexadecapole one. And if you remember from what I've told you before, you need the lower the multiple of the mode, the higher the angular velocity you need for the mode to become unstable. So this is why the L equals 4 window is lower than the others. You can do the same about the R mode. Here, as you can see, for the F mode, the windows are quite small, so you still need to be around 90% of the Kepler limit, of the mass shedding limit of the star to make this instability work. For the R modes, if you also include viscosity, the numbers are much, much better, and you can get very, very big instability windows. And it was suggested that the R mode instability could be an explanation for the fact that we don't observe any pulsars above, well, currently it's 716 hertz, but in general, we do not observe many fast rotating pulsars. And this cutoff, this 716 hertz, is much lower than the theoretical upper limit. So our theoretical upper limit is basically the Kepler frequency, the point at which the star starts destroying itself. And people have been wondering why this is. Why don't we observe pulsars rotating closer to this limit? And one suggested explanation is that as the star enters the instability window, it spins down. And here is how it works for an accreting system. So if you have a star at this point, at point A, spinning at some frequency with some temperature here, then because it is accreting, it will spin up due to accretion. And then when it enters the instability window, and the mode starts growing and growing, the oscillation will heat the star up. It will move it further inside the window. And then at some point, the instability, we think, that has to reach some saturation point. So the mode cannot grow forever. Something has to stop it. And the main suspect here is non-linear effects. So basically, the oscillation mode that becomes unstable couples to other modes of the star, and it drains its energy through these modes and stops growing. And depending on how high this saturation amplitude is, you get different curves here, but the idea is the same. So when you reach this point, then your star starts spinning down because it emits gravitational waves. And then the cycle completes by the star cooling down, and the cycle goes on and on. So that's what people have suggested is the explanation behind the lack of pulsars spinning above this limit. But there is also a problem with that, which is that many of the accreting sources that we see in the universe lie inside the instability window of the R mode, or at least what we expect to be the R mode instability window. And this is a problem because we expect these two phases, B, C, and C, D, so the heating and the spin down, to last not very much. So statistically, it would be much more likely to detect a source in these two phases, the cooling phase or the spin up phase, which last much, much longer, at least according to models, but not in these phases. So it's a mystery why these sources lie inside, why so many sources lie inside the window. And the most plausible explanations for this, the two most plausible explanations for this are either that the R mode instability window is not what we think it is. So there are other mechanisms, other viscosity sources that make the instability window smaller than this. And for example, you can account, if your star has a crust, you can account for the viscosity between the crust and the core of the star. And in this case, your instability window becomes smaller but this explanation doesn't satisfy many people for various reasons. The other explanation is that your saturation amplitude, so the highest amplitude that your unstable mode can reach, is actually very, very low. And what this means is that if it's very low, the spin down phase here will be very, very long, because the lower the saturation amplitude, the less efficiently the star emits gravitational waves. So it will basically stay inside the window for much longer. But unfortunately, for this, we need an accurate calculation of the instability saturation. And there have been efforts by people, including myself, for this. But for the moment, it's all done in Newtonian gravity and with a minimal number of assumptions that for not so realistic neutron stars. So it's quite hard to say whether this is actually the answer. But in any case, the saturation amplitudes that we find are low enough, but not as low as required for to explain the presence of these sources inside the window. Okay, so that's about it about the gravitational wave instability. Now I'm going to devote one slide only for the viscosity-driven instability. And the reason for this is, as opposed to the gravitational wave-driven instability, the viscosity-driven instability is not generic. So it was first demonstrated by Robert Stewardson in the 60s that such an instability, the viscosity-driven instability that was known for many, many years, can be accounted for by the prograde F mode. And there is a similar instability criterion as before, adjusted. Now we need the star to be stationary on the rotating frame, remember, not in the inertial frame. But this instability is not generic, which means that you cannot always find a mode that becomes unstable at any rotation. And it's basically only relevant for the prograde quadrupole F mode, the one we talked about. And this is the most recent work that I could find on the subject. And as you can see, the angular velocities for the various equations of state here, the angular velocities required for the star to become unstable to viscosity are very, very high. So they're, the lowest one I can see here is 93% of the Kepler limit. And not to mention that, like the gravitational wave instability is suppressed by viscosity, the viscosity-driven instability is suppressed itself by gravitational waves. So this makes the situation even more difficult for viscosity to actually play a role in the evolution of the star. Okay, and for the final part, I'm going to tell you a few words about my most recent work, which is basically it's a variation of the CFS instability, of the gravitational wave-driven instability, that is, but applied in binary systems. So instead of having a mode, now we have a tide, if you can picture this. So we start with a star rotating with some angular velocity, but now it's perturbed by a tidal potential of an orbiting companion. So if we don't have a binary companion, then this side is 0, and then we're back. If we solve this equation, we will take our solutions will be the oscillation modes of the star. If we include the tidal potential, then we have a driving force on the right, and if we treat it as such, we again take a perturbation, but now it's a forced perturbation, and it's basically the tide. And if we calculate again, like before, the energy rate of the tide, we get something like this. And for a binary in a circular orbit, this should be positive. So the energy of the tide should grow due to orbital shrinking, because as the two stars orbit each other, they emit gravitational waves, they come closer and closer, and the tide grows, basically. So now we ask the question, what happens if we take into account gravitational wave emission from the tide itself? So not from the binary, not from the stars orbiting each other, but from the tidally perturbed star itself. And to do that, because we are in a Newtonian context, we have to take into account an extra driving force of some sorts, which takes into account the emission of gravitational waves. And this term is added up here as well in the energy of the tide. And now if we calculate the energy rate of the tide, including the contribution of gravitational waves, we find a formula which is, might remind you of the formula we had for modes. So this is the orbital frequency, and now here we have the orbital frequency minus the angular velocity of the star. And if this product here is negative, then the energy of the tide due to the emission of gravitational waves will grow, will increase. And the condition here, the instability condition, is that the tide on a rotating star becomes unstable to gravitational waves if the angular velocity of our star is larger than the orbital angular velocity. And what this looks like, if you can picture it, if you look at the tide, if you look at the tidally perturbed star from a distance, you will see that it's always prograde. So it's going against rotation. But in the rotating frame, it appears retrograde. And this is similar to the situation we have with unstable F modes. And this is another alternative to write the instability condition, which I think looks rather nice. And to show you some numbers for this and to check if it's actually interesting, we take a simple polytropic model with some typical values of mass and radius. For simplicity, we assume that the orbital angular velocity and the angular velocity of the star are parallel, and we only take the quadruple components of the tide. There are higher order components, but these are the best gravitational wave emitters anyway, and they are the ones that prevail during the in-spiral. And if we do this, when we calculate the instability growth time, we find such a formula, and this is plotted here. So I'm going to try to explain this plot because it's a bit messy. Here we have the orbital distance between the two stars, normalized to the radius of the star. And here we have the angular velocity of one of the stars that we're looking into, the one that becomes unstable due to gravitational waves. And all the colored area is the area where the instability is actually active. So as you can see, the instability is sort of generic. So there is a very small area where it's not active. However, the instability growth time is typically quite big. So it could become significant only close to merger. So as you go down this plot. And even this, though, is not enough if your in-spiral is faster. Because if your stars merge before your instability has time to evolve, then it doesn't really, you don't expect it to contribute much. And this is what is shown here. So this is the in-spiral time scale as a comparison, and the darker the color, the shorter the time scale. And as you can see, quite much everywhere, the in-spiral time scale is shorter than the instability growth time. So at least in this model, and again in a Newtonian context with simplistic arguments, we don't really expect this instability to be really significant. There was a recent publication by Kostas Kokodas and Anton Suvorov, who mentioned briefly that in a model they considered this is not the case, and the instability timescale is faster than the inspiral. But I have to check this more. I admit I didn't. I don't know how they produced this result, and I have to look into this. And in this plot, we don't include the mass ratio at all because it doesn't really affect the result. There may be ways to make it affect the result. So here we consider a neutron star binary, basically. There might be a case where the instability gets much faster if the companion is not a neutron star. So if it's a much heavier object, then there might be a chance for the instability to actually play a role. But then for this, you need to take into account more things than this simplistic model. And this is left as work for the future. At some point, I will look into this. However, even though the instability, even though we said that the instability is not really expected to make a big, to influence the system a lot, it might still be worth out checking whether the accumulated effects of the instability make a difference. Because yes, the instability evolves slowly, but if the inspiral takes a long time anyway, then the effects of the instability might be accumulated, and then near merger, where our detectors are the most sensitive at the moment, it might have an observable effect. And for this, we used some simple energy and angular momentum conservation arguments. So basically, the gravitational waves that are emitted from the system should be taken from the orbit, from the tidal perturbation, and from the background of the star. These are the sources that have to balance the gravitational wave emission. And if we do that and we solve for the orbital separation rate, this d prime here, we find that the instability comes in at second order in this parameter epsilon, which is this one. So this involves the love number, the tidal love number. For those of you who don't know, the tidal love number is a measurement of how much the star can deform in the presence of a tidal potential. So if it can deform a lot, then the love number is high. If it cannot deform a lot, the love number is not high. And this depends on the equation of state of the star, basically. And here, the first term is the inspiral point mass limit. So if you just model your two stars as 2 point masses, if you take if you consider one of the two stars to actually have some size, to be an extended object, then you get these first order corrections, and these are known for a long time. And due to these correction, you can find that the inspiral is actually accelerated. And this is expected because some of the orbital energy goes into the tide. And now the second order corrections are due to this instability, and you can find that due to this, the inspiral is now decelerated. So it has the opposite effect of having just an extended object. And you can work this out by calculating the orbital cycles that the system takes until it merges. And you can parameterize the corrections like this, and they are plotted here. So you have less orbital cycles if you take into account just an extended body. The inspiral is accelerated. And if you take into account the instability, then the orbital cycles increase. They don't increase by much, admittedly. It's a very low number, but maybe with next generation detectors and with more realistic models, this there could be a chance that this could be taken as a correction to the gravitational wave signal that we see now. And it also, I also calculated how it affects the spin of the star, and also near merger, very close to merger, the spin goes down by also a very little bit. Okay, and instead of showing you any conclusions, I'm going to show you a nice representation of a gravitational wave signal that you get from a supramassive neutron star, which evolves throughout the instability window of the quadrupole F mode. So what I'm going to show you basically is, if I go back here, what you expect the star to do here is when it's newborn, it's very hot, so it will cool down, it will get inside the instability window, it will keep cooling down, and then after some point it will start spinning down until it exits the window. And if this star is a supramassive neutron star, so if it's a star that is born after the merger of two other neutron stars, then if it spins down enough, it will just collapse. And this is how the gravitational wave signal translates into music. And I will also try to play it. If it comes through my microphone, that would be cool. So yeah, sped up, obviously, not very fancy, but it was nice. Thank you.
Okay, thank you very much, Pantelis. Okay, so I'm sure there are questions related to this nice excursion on neutron star physics, their oscillation modes, their tides, and how you can do astrophysics with them.
Yeah, I have a question.
Okay, go ahead.
Yeah. So at the beginning, when you talk about the slow rotation approximation for the L equal 2 modes, the splitting of the various different M modes.
Yep.
Yeah, can you go back to that plot? Yeah, so here, you said that you calculated this up to second order in the spin. But then what is the error that you make around this Kepler frequency? Is it small or big? It's like, how much can you trust this expansion?
For second order, if you go that high up the angular velocity, the error is quite big.
Okay, so it might be that you don't go negative with the frequency, or you know that you can always go thanks to the thing you said about the Schutz paper.
No, actually, people have made actual calculations of this without using the slow rotation approximation. If anything, the slow rotation approximation underestimates this point. So
okay.
If you get this with the slow rotation approximation, with actual calculations, you should be more to the left. So your mode should become unstable earlier.
Okay, okay. Thank you.
Okay, anyone else? Okay, I have a question. So related to the tides and the binary. So for LIGO, this seems to be an effect that just is hard to measure at all. But if you would think about an emery, where you have a neutron star, for example, and a supermassive black hole, how do you think would this change?
So if your companion is a black hole, you mean?
Yes, the supermassive black hole. So if the mass ratio is very large and if it's a black hole, yeah.
Yeah, that's a good question. The problem is that well, the reason because this calculation is easy is because for neutron stars you can come as close as you get. So here I stopped at 3 kilometer at 3 radii apart. I considered the merger to be three radii apart. If your companion is a black hole and even so a supermassive black hole, then you would have to take into account tidal disruptions and stuff like that. So even if you had an instability at some distance away from the black hole, I don't know how close to the black hole you could get, because you also need to, from this plot, you can see that you need to be, your two objects need to be close to each other to get significant, to get low enough timescales. So yes, the mass ratio will probably make the timescale lower everywhere, but I don't know if it's going to be low enough further out where the neutron star is still an entity. You know what I mean? Because
yeah, I think so.
If it gets close, it's going to be tidally disrupted, and then we're going to have something else.
Okay, thanks. So anyone else?
Can I perhaps ask something? I'm John Miller. I'm connected from the UK. I want to ask you about this object which is in the mass gap. Either the very light black hole or the very heavy neutron star that you were mentioning, coming from the LIGO source.
Yeah.
I don't know anybody that thinks this is going to be a neutron star, because it looks so probable that it's a low mass black hole. After we know about GW 170817, almost everybody thinks that that eventually produced a black hole of almost exactly this sort of mass. And the thing looks so probable as the source of this object that it looks a bit strange for people to be excited about the possibility that this could be a heavy neutron star, which has enormous problems from the nuclear physics point of view, unless it's some exotic object. I don't know what you think about this.
Well, given the fact that, as far as I know, they didn't see any electromagnetic counterpart, then yes, I guess the most probable explanation is that it is a black hole, but you know, the community likes to be excited about possibilities, and 2.6 is probably too low for a black hole anyway. And people have started saying, what if it is a neutron star? But I agree with you. It's most probably it's a black hole, but it's definitely not for sure yet.
You see, the point is, we think we've seen one of these black holes being formed. And it was 170817. If this produced a black hole at the end, then that's what the mass would be. So it looks so plausible.
Yeah.
Yeah. Anyway, there's been a lot of discussion about that here.
Maybe you're right. Yeah. I mean, then I guess you would have to consider the possibility that this is a black hole that was already the product of a neutron star binary merger in itself. Yeah. I mean, the possibilities are open, I think.
But because people talk about this as being a second generation black hole.
Yeah.
From this point of view, and you know, there's been some excitement in the literature about that possibility, and talking about whether you really think that a black hole formed in that way could then find itself as the member of another binary system with this rather heavy star, and there have been people thinking about all sorts of aspects of that.
Yeah, I mean, it's definitely an interesting discussion, but I'm also I think it probably is. I mean, the explanation that it is a light black hole is for me more likely than it being a heavy neutron star. But you know, we don't know. It could also be a very, very fast rotating neutron star that can actually support such a high mass. But there are other factors suggesting that this is probably a black hole.
The other thing I wanted to ask is that something else which is in play in this story is the possibility that you have a distortion of the crust. This is the story of mountains.
Mm-hmm.
And just recently, I've been reading a whole lot of literature about this. And I know that some of the LIGO people involved on the experimental side are very much looking into that sort of story for continuous sources.
Yeah.
And they're doing searches for continuous sources, which I gather is now becoming quite a big industry of LIGO people. I hadn't realized that until very recently. This is another reason why you could get the spin up stopped before you get to the shedding limit. Namely, that you get a distortion, and that's the thing that stops it.
Yes.
This is the Buildston story originally.
Yes. If you have a mountain, the same thing can work, yeah.
So as far as the gravitational wave people are concerned, there are various different pictures that they're interested in, I think, with this.
Yeah, the problem is that there are uncertainties pretty much everywhere. So for the R mode, we don't have a very accurate idea about the saturation amplitude. So we cannot really say what would happen. And for the mountains also, you also need some numbers. So people usually constrain this with the ellipticity of the star. And then again, you need an accurate determination of how large the mountain can be on the neutron star. So if you tweak the numbers, then you can prove anything you like with either scenarios. But I guess that's exactly the reason why people look into this stuff so much now. And the LIGO people are obviously going to be more and more interested in this, because the continuous signal is probably the next thing to detect.
Thank you, Marissa. I enjoyed your talk very much because it was a bit nostalgic for me. I thought about these things many years ago, back at the beginning of some of that story. So I was very interested to hear it.
Thank you.
Okay, if there are no further questions, then yeah. Okay, no questions. Yeah, then I want to thank you very much again, Pantelis, for this very nice talk and being here for the questions. And that's it for this week.
Thank you.
Bye-bye.
Bye-bye.